So first off, thanks everybody for coming to my talk about compilers, virtual machines, and code analysis, what makes Dart and Flutter run. It's nice to see that so many people show up to, I'd say, such a niche topic. Hope you had a great day of the conference already. There we go. First about me, my name is Norbert. I'm a freelance Flutter software developer. Even though I mainly do Flutter, I do a lot of different things. And I've always been interested in things happening under the hood. Pretty much since the beginning, when I first found Flutter, I was interested in how does the layout stuff work, how do render object widgets and stuff work, which I did a talk a couple of years ago. Over the time, I also built a couple of tools, open source project, Flutter IDE, which I was working on quite a few years ago, which was a huge undertaking. The Detective, which was this real-time debugger for your app. And currently I'm building on this small toy project called Widget Preview for Flutter to showcase widgets in isolation without having to write any wrapper code. And these projects kind of show I always take a look at what's possible in Flutter, what can be done, and see how that can be used to build something cool. But this talk is about compilers and things. So in the first 40 minutes, we're gonna understand how computers work on a very most basic level. So we'll have to spend a lot of time on understanding every bit and piece. Of course, I'm joking. It's actually pretty simple how computers work. A lot of things that are happening are mostly optimizations or some hardware things that need to be done. But the concept pretty much is we want to perform some action based on some data. So a computer works by reading an instruction and based on the instruction executing some code, which may in turn write some data, perform some binary operation, and then continuing the cycle. But when we write code in Flutter or Dart, we don't usually think about binary opcodes and registers and things. We think in classes, we think in statements and expressions, in method invocations. So now we have this disconnect. We have this high-level code that is happening in Dart, and we want to generate some machine code or something the computer can understand. And there's a couple of ways this is usually done in modern or even in generally languages. And I want to briefly talk about these. First off, we have the first example of programs being interpreted. What does interpretation mean is that we kind of treat code as some form of data. The code is taken and some other program executes the code based on what it says. This is pretty abstract and high level, meaning we have to write a program to execute another program. And it's generally pretty slow because there's a lot of indirection, a lot of things being indirect to what the actual computer, the CPU, does. Dart currently doesn't do any interpretation in its pipeline. That would just be too slow. Next up, speaking about speed, is AOT compilation. AOT compilation is, as a lot of you probably already know, used for release builds. When you release an application to the App Store or the Play Store, an AOT compilation is done, meaning the code is taken and before executing it, some machine code is generated in this intermediate step, and this machine code can then be executed. This has the advantage that we don't have any indirections between another program needing to interpret it or doing some indirections. We have raw machine code that can be executed by the CPU directly. I talked about CPU, and there's different CPUs. There's RISC, there's ARM, there's x86. And that means machine code generated with AOT is platform specific, architecture specific. Each of these instruction sets have different properties and instructions that can be used. So the AOT compiler of Dart has to generate machine code for every single architecture there is. Luckily, the Dart VM or Dart itself implements a bunch of different architectures to compile to. That's why you don't really have to worry about what's going on in there. Next up, we have just-in-time compilation. And just-in-time compilation is first hearing about this weird mixture of ahead-of-time compilation, kind of some sort of interpretation. First hearing about it, it's like, why would you ever do this? But basically what's happening is the source code is taken, instead of being fully kind of interpreted or directly compiled to machine code, a compiler is shipped with the app. And that compiler, it converts to machine code, but it does so on the fly. So when you first start the app, it takes a look at the first function that is executed, writes some machine code that is being executed. This machine code is first not optimized. And based on runtime information, it analyzes and looks at the code that is being run. It then can decide, yeah, let's further optimize this function to make it more quick based on usage, or also decide on heuristics, like this function makes more sense to be, I don't know, inlined or put into a different function. And the just-in-time compiler also enables stuff like hot reload, because we have a compiler in the app and we can push code to replace function definitions and different things. I also already mentioned this, but I want to take a look at a couple of things Dart does and Dart uses. So when you do Dart run, it runs your source code, but internally it does a bunch of different things, and this is the JIT compiler. So you run a program, it just-in-time compiles stuff as it is needed, and the Dart run function is basically a nice, convenient way to run a program. Then we also have the Dart compiler AOT snapshot, which is, as I mentioned before, compiling ahead of time to raw machine code. The difference here is to something like Dart compile exe, that it compiles without the Dart runtime. It just compiles your code. So this standalone code cannot be executed because there's parts missing. Most importantly, the garbage collector. For example, because your code alone cannot work, there's a bunch of garbage being created with stateless widgets being created here and there. And to run an AOT snapshot, you need to run it with a Dart runtime. This is also platform specific. As I said, the exe is pretty much the same, but it includes the runtime. The difference is it makes the size a bit bigger because there's more code in your application. There's JIT snapshot, which is kind of weird because you would run a program with JIT anyways. Why would you do a JIT snapshot? The idea behind here is that you run the program with some training arguments, and it will then pre-optimize some code and see, okay, this is how you will run the code usually. And next time you start it, you already have some pre-compiled machine code, so you don't have to go from nothing, basically. We can transpile to JavaScript. That's how it runs on the web. It takes Dart and generates new code in a different language that can be then executed in modern browsers. We can compile to kernel, which is this intermediate language, which we'll dive deeper in a couple of slides. And you can also compile to WebAssembly because of the new WebAssembly garbage collection implementations that a lot of browsers now support. Before, WebAssembly didn't really support garbage collection, meaning that languages that rely on garbage collection had a hard time to kind of compile to it. But now Dart is working on that. So we talked a bunch about how or what the concepts are, but how does this really look like in Dart? You may have heard the terms frontend and backend before. If you're building apps, you usually call the app itself the frontend, and the backend is usually some server. When building compilers, these names are used differently, which might be a bit confusing, but in this case, the frontend is basically the piece of code that usually takes care of the first steps by taking text, which is source code, and converting it to some more usable representation. In this case, it is this intermediate representation called the kernel, which is usually saved with a .dil format. And it basically is just a serialized, binary serialized abstract syntax tree. This word, if you don't know these words, we'll talk about abstract syntax tree in a couple of slides. Then this kernel is taken and given to the backend, which is the Dart VM, which then can do JIT compilation, it can do ahead of time compilation, and it can do a bunch of things with this. Before we go to the backend, let's see what responsibilities and things the frontend does. And just if you spend a bit of time with compilers before, you probably know these steps. The first part usually in a compiler, and what is also being done in Dart, is tokenization. So you have a very messy structure where it's just characters and it's kind of hard to work with. So the first step is to simplify it by just mapping the string into tokens. So we have a void keyword, we have a main identifier, we have symbols, which are parentheses. So this just makes it simpler for subsequent steps to work with. Next up is pretty much where the magic happens, the parser. The parser takes these tokens, and you can actually take a look at the grammar of Dart, which is basically the rules on how you take some stream of tokens and convert it to a structured tree, an abstract syntax tree. Why trees? Trees have some nice properties where you can do a bunch of cool things with them. Let's consider this simple example of a statement, which is 42 plus 8. And if we were to convert it to an abstract syntax tree with a parser, it could look something like this. We have a parent, which would be a binary expression. And the binary expression has two operands, the left and the right one. In this case, the left one is an integer literal, the right one is an integer literal. If we wanted to compute the value of all of these, it would be pretty trivial to go forward. 42 is an integer literal. We know the value is 42, 8, 2. And to evaluate the binary expression, all we have to do is evaluate the left and right operand and add those two together. I want to illustrate that at this point, we add another 42 to our statement, and then the tree might look something like this, or you can just do the same algorithm to kind of resolve this tree and evaluate what's going on. A couple of other interesting things the front end does are things like type checking, making sure that all the types line up, that you don't assign a string to an integer. It does some type inference, where you say it's a final or a var without explicitly specifying what the type is. So it can infer the type of it by looking at what the other side of the equal sign is. And it does a bit of desugaring, where it just makes the languager simpler to work with in subsequent steps. So the backend doesn't have to implement every single language specification because they have been simplified to something else. And the result of all of this is just this kernel file, which is the two things that glue together the front and backend. If you're interested in compilers, interpreters, and all of this nice stuff, there's a great book by Robert Nystrom. I've read it a couple of years ago. It's very well written. It's actually free online that you can check out. And you can also buy it as a book. It's about crafting an interpreter, taking a fictional language and going through tokenization, creating a parser, and doing some cool things. So, front end. Let's check out the back end. And here is kind of where some magic is happening. Not really magic, but here is where we leave the Dart world. I forgot to mention the front end is fully written in Dart. So everything you see in the front end, you can check out in the Dart SDK. And I'm not too well versed in C++, so I'd rather take a look at Dart code. So the front end is a nice place to check out. The Dart backend, on the other hand, also called the Dart VM, is written in C++, but even that is in the Dart SDK. So I won't dive too deep into this because first off, it can get really complicated. Machine code is hard to read and understand. And frankly, I'm no expert in all of this. There's a lot of intricacies and a lot of things to care. But I want to show you a small example of converting some code to, in this case, ARM64 machine code. ARM64 because I have a MacBook M1 and compiling here creates that kind of code. So let's consider the function test, which takes an integer I and defines two variables, A and B, adds those two variables onto I and returns the result as C. That's the function, but you may have noticed there is a weird for loop at the top. And we do this because in this case, we want to take a look at some optimized code. Optimized code is a bit slimmer to look at. It's less code. It already does some, removes some redundant checks and so on. And to force the JIT compiler that we're using in this case to optimize this code, we just invoke this function a bunch of times. And this will signal to the compiler, hey, this is some important function that we need to make sure is optimized. And then we can take a look at a bit of assembly-like code. So that's a really fun thing to do. You don't have to build the Dart SDK. You don't have to do any magic. You can just use Dart as a command line tool and add some weird-looking arguments. More specifically, there you can see we specify we want to see optimized code, so it only looks at that. And then we can run this. And this will result in a bunch of output, but it will include this machine code. Looks daunting. Frankly, I don't understand every single instruction in here, but I want to give a quick update on how this looks structurally. So at the very beginning, we have some code related to invoking the function. This makes sure that the frame is set up. This makes sure that the value of I is copied over to some memory space. If we look at this specific code, it on the left, it loads the value of I into the register 1. These two code blocks are not synchronized, so just imagine they were. And in here you can see the whole function that we implemented. The 3 lines of code are condensed into 2 single lines. And more specifically, it's pretty much just a single line because the compiler was smart enough to figure out A and B are constants, and we just want to add them to I and return that. So it does, it adds the hexadecimal value 4 to R1 and saves the input at the output in R0. So you may be wondering why it says 4 and not 2. I was wondering too, and I had no clue. I reached out to Slava on Twitter and asked him, so why is this happening? And he explained to me that it's because Dart uses the least significant bit for tagging if the value is boxed or not boxed. And to make space for that value to be 0, integers are shifted to the left. That means multiplied by 2 to make space for that. That's why it says 4, but in reality, this integer means 2. And at the end, we have some code related to returning from this function. And also in this code, it just checks if it's overflowing. If it is, it jumps to some memory address and does some magic. So that is pretty much the actual code that is running on your computer that you can take a look at. It's really interesting to see, like this is as low as it gets. This runs on your CPU. This is pretty much everything that this function produces. Quick side note, because I find this topic really interesting, about bootstrapped languages. So a bootstrapped language is a language that is implemented in itself. So you might be wondering, how can a language be implemented in itself if the language isn't implemented? So the way this usually works is you write a new language, you have a great new idea. So you write a compiler for the language in another language that already exists. And once you have the first version of your language running, you can just write a new compiler in your own language, which then compiles a new version of that language, and voila, you have a bootstrap language. Here's a couple of examples of languages that did that. Dart itself is not bootstrapped, so even though the front end is written in Dart, the back end is written in C++, and it would technically be possible to rewrite it in Dart, but what's the point if it isn't really needed right now? But I find this really fun to think about having a language implemented in itself. So I talked about a bunch of theory, so let's get a bit more practical to not lose everybody. As I said, the front end is written in Dart, and you can actually very easily play with this front end. There's this package called Analyzer, which uses the things the front end does and allows you to analyze Dart code. And it's on pub, so you can put it into your web, desktop, Android, iOS application with your usual syntax that you use in pubspec.yamos. And after that, you can start analyzing some code. It's pretty simple. You have to do some setup code where you just specify some paths it can use, some paths it should exclude, and a path to a file that you want to analyze. And at the end, it gives you back an abstract syntax tree that is a fully resolved tree that you can traverse and do things for the different kind of nodes. So knowing that, let's have some fun. And what else? I talked about bootstrap languages. I find the concept pretty fun. Let's implement Dart in Dart. A quick side note, we're gonna do a bit of live coding. And I will be implementing a simple tree walking interpreter. So this is an interpreter. That's mostly for academical purposes, but I find the example really fun of what you can do with these tools that are out there that you can add with a few lines of code. So there we go. So we have a main function with our normal Dart program. We have already set up the dependency, and now we can start analyzing some code. I wrote a helper function to kind of do the few lines that you saw before, and we can write that with this code, I call it get resolved unit for code. So we're passing a string where we have a Dart program that is valid. And in our simple interpreter, we want to implement calling functions. More specifically, we want to be able to call print. We want to do some binary expressions. And we want to be able to print hello world, as every good language should be able to do. When working with abstract syntax tree, one pattern that is usually used is so-called visitor. That may seem daunting sometimes, but they're actually pretty simple. They allow you to execute some code for every single type of node there is. You can imagine there's a lot of different nodes in Dart. You have binary expressions, you have integer literals, you have function invocations, you have class declarations, and so on. But with the visitor pattern in this case, we can just implement the specific nodes that we want to work with. And in this case, the very first thing we might want to do is find the main function that we want to call. So for this, we write a simple visitor, which in this case is a recursive abstract syntax tree visitor, which just makes sure it traverses the tree recursively. And just take a look, is the function declaration that we're visiting the main function? If it is, we're saving the value, and then we can instantiate that and just make the resolved unit that we just analyzed accept this visitor. We have a main function, and now we want to actually evaluate some code. For this, we're going to implement another visitor, which we call the evaluating visitor. Again, it's a recursive abstract syntax tree visitor. And let's start with the simple things. If we want to evaluate an integer literal, so the number 42, for example, the result of evaluating that is 42. So we can do that for integers and strings, for example. We just evaluated both of those and return the value. Afterwards, we also want to support operations, binary operations. And for this, we can do the same. We just visit a binary expression, and we evaluate the left operand, we evaluate the right operand, and then based on what the actual operation is, we just perform the operation. This is all pretty simple because the languages we try to interpret with the language that we're trying to interpret is the same, so we don't have any different concepts. We could implement most of the language in a fairly easy manner because all of the concepts line up. Stuff like this gets a bit more complicated if the two languages differ by a lot, because then you kind of need to find a value, a way to bridge the difference. Last but not least, we need to implement method invocations because we want to be able to print. In this case, we just check, are we invoking a method that is called print? If yes, we print. If no, then we just ignore it. After all of this, we can do main function dot accept and the evaluating visitor. And if the demo gods are with me, we can execute this code and it should run this string as code that we just did. Yay, it shows hello world and 9. Just as a way to show you that this isn't hard-coded anything, we can, I don't know, put in any weird number and it should reflect a new value that executes this. Yay, you can check if that's correct, but it should be. Cool. Then, so this was a very simple tree walking interpreter. You would never really implement something like this. And while researching for this talk, I found a package that is called Dart-eval, which is pretty fun. It implements a bytecode interpreter, which is very similar. But first, before executing it, it creates some sort of bytecode that is very similar to what the Java virtual machine does and executes that. It's still interpreting it, so it's not generating any machine code. Yes, that's one way to improve performance by quite a bit. With this, you could, for example, push code to your application. And if you heard about pushing code, another practical use case that this kind of system allows is building something like Shorebird. So looking at the public docs there is, Shorebird kind of does some very clever tricks and things, but internally it ships an interpreter to run code that is being changed in a very clever way. So we talked a bunch about what happens before and during Dart is compiled and being run. Let's look at what happens after Dart runs and what enables some of your favorite tools and things with Flutter. When running a macOS application or applications in general, I think you may have noticed this debug services listening on and then an address to some weird WebSocket. And what this actually is, it is the VM service protocol running inside the Dart VM, giving you access to a wide variety of different things to do inside your application. You can add breakpoints, you can reload your app, you can evaluate Dart code as a string, and you can access all of the things inside your application from the outside. And this is also what powers, for example, the Flutter inspector. The Flutter inspector, if you open it, you can trigger methods such as slowing down the time. You can show boundaries. You can see what the widgets that are currently being shown have as properties. And this is all possible by using the Dart VM service protocol, by listening and reading what is happening inside your app. I also built this fun little desktop application, which I call Detective, which does the same thing, but in real time. So it allows you to listen to things inside your applications without setting breakpoints. In the short video I did back in the day, you can see that on the right there is your target application that you're working on. The left is Detective, and it connects to that application. You are able to invoke different things. You can listen to stuff as it is happening in real time. Again, this is pretty simple to use. It's just another package on pub, which is called VM service. You can add as a normal dependency in your application. Keep in mind, only the just-in-time compiled version of Dart, meaning the one that is for debug builds, includes this Dart service protocol. And you can then, with just a few lines and a bit of setup, which I don't want to bore you with, you can read it online. It has some nice documentation. You can connect to your application based on this URL, and then you can do fun stuff. So we're on Fluttercon, and I talked mostly about Dart up until this point, but I also want to talk a bit about Flutter and why Dart and Flutter is such a great combination. So who has seen this diagram before? Okay, pretty much everybody. This diagram kind of shows the different parts and components of how Flutter is architected, but I was curious what happens between foundation and the engine. Like, how do the two things communicate? What happens? What is being done on the Dart side, and what happens on the Flutter side, on the engine side? And for this, I wanna quickly. How do I close this? One sec. There we go. So now I need to mirror. We can do this. And mirror. There we go. Sorry, unexpected. Okay, you can see perfect. And so for this, I want to take a quick look at what happens when you draw a container. So we have this new project, which I just created, a Flutter Run project. And in here, we have a container that we are drawing. And let's take a look at what happens inside the framework for this container to be drawn. So for this, Flutter is fully open source, and we can just go into the class definition and see what is happening. So we see, okay, the container is a stateless widget. We know stateless widgets don't really do anything themselves, but they delegate to some other implementation. So we can scroll down a bit and check the build method. We can see, aha, okay, the color is not null, so it has to use some sort of colored box. And then again, we can check out what the colored box does. Okay, the colored box is a single child render object widget. So this is already going a layer below the widget layer where we do reactive things and have all the fun. This is the render object layer that we should hopefully not have to touch too often. Then we can check out, okay, we have a rendered colored box. Okay, the rendered colored box is a rendered proxy box with hit test behavior. The names are quite a mouthful, but this just does some utility things to size and position and whatnot. The interesting part is looking at the paint method. So the paint method actually just calls draw rect on canvas. So this bridges the world of reactive layout and all the fun stuff to drawing on a canvas. So when we draw on a canvas, we can check out what's happening below, and then we can go into the native canvas. And inside the native canvas, we can go to draw rect. And eventually, of course, the framework does a bunch of things, compositing everything, running a frame, and so on. But eventually, draw rect is being called. And we can see there's no implementation for draw rect, and that's because that is a foreign function that is implemented in C++. And this kind of leaves the Dart Flutter world where we all live happily. This goes to the sometimes scary place of C++. So let's try to get back to the slides. Okay, back at the slides we are. Cool. Yes, we took a look at the container. So you may be wondering, okay, what happens next? We leave the Dart world. We're in C++ now. I don't want to dive way deeper into that because that's where my knowledge also fades a bit, and I am not too versed in this, and that gets a bit more complicated. But basically, it boils down to using Skia. You may have heard Flutter runs on Skia. And by looking at the website, Skia is an open source 2D graphics library which provides common APIs that work across a variety of hardware and software platforms. That means Skia is kind of this library that makes it easier to work with graphics, working on different platforms, on different hardware, on different graphics cards. And that's what Skia does. And Impeller is the new thing the Flutter team has been working on. The idea behind Impeller is to fix a couple of issues. For example, the shader compilation in Skia, it happens on demand. Shaders are these things that run in the hardware to actually draw pixels. In Impeller, they can be pre-compiled. And Impeller does a bunch of cool things, but it also does 3D. So Skia is explicitly 2D, but Impeller can, in theory, also do 3D. But even those are libraries built as some code. What do they do? So we need to go even lower. And to go even lower, we have to go to pretty much bare metal. And there we talk about graphics APIs. These are the things that kind of are implemented by your graphics card that allow you to talk to it, to give it commands, and to draw things to the screens eventually. These are things like Metal on Apple, OpenGL, that is this cross-platform thing that also works with, on the web as WebGL, and Vulkan, which is this newer, cool thing that gives you more control over the graphics card. And you may have heard about these before. Games also build on these. So if you want to build something to draw pixels, you have to build on these graphics APIs. And that's exactly what Impeller and Skia also does to allow you to draw pixels. Skia, an example, it builds on top of this 3D available thing. You can do 3D graphics with OpenGL, but Skia just restricts it to 2D. And Impeller pretty much is a drop-in replacement eventually for Skia, but in theory, you can also do 3D it by exposing the APIs from these. That's it. Thank you very much for listening. And if you have any questions,